Hey everybody, so here we are at 6.6 on solving exponential and logarithmic equations. So we're looking at how we can solve an exponential and a log equation. That's what we're going to be learning here. We're also going to be looking at the very end kind of at some inequalities as well, which are going to be very similar to the equations. But first let's do a little cartoon, a little in the bleachers. So out there on the football field. So we won't know until the MRI, but I'm certain that it's either a ouchie or a boo-boo. So a big football player either has an ouchie or a boo-boo. Alright, so let's go on to our first little core concept there on page 181. And this is our property of equality for exponential equations. So just like regular equations, we have properties of equality, or whatever we do to one side, we will do to the other side. It's always the golden rule of algebra. But in this one, we can see that really the example is going to be the one that's the most helpful, I think. But you can see it over here. It says if b is a positive real number other than 1, then b of x, or b to the x power equals b to the y power if and only if x equals y. So notice that the b's now are gone, the bases are gone. The exponents can equal each other. Same thing on this example. If 3 to the x power equals 3 to the 5 power, then x equals 5. The 3's, these bases, are gone, and the x can equal 5. The exponents will equal each other. So if you have the same base, then your exponents can equal each other. One reason why, basically the reason why that's true, and why that is because of the inverse properties that we've already learned. So remember, if we want to get rid of, if we're trying to get the x, or free the x here, we need to get rid of this 3 as a base. So that means we would kind of zap it with a log of the same base. So we can actually zap this with log base 3. So I could do this here to this right here, log base 3. But whatever I do to one side, I will do the same to the other side, log base 3. And so now log base 3 will cancel the 3 there, that base 3, leaving just the x. And over here the same thing will happen with log base 3 will cancel base 3, leaving just the 5. So that's why that's able to happen, is if you do have the same base, your exponents will equal each other. So during this lesson, I'm not going to do this very often, where I'm going to put the log base, of the same base to cancel that out, unless it's only going to be done to one side, and I need to actually have the log on the other side. But we're just going to realize that the base 3's can cancel each other. Alright, so let's move on to try some problems here. Okay, so here on page 182, our first 3 problems in the extra practice, we're solving the equations. So here we see on number 1, we already have base 5 on this side to the exponent of 2x plus 4, base 5 on the other side to the exponent of 5x minus 8. So we could zap both sides with log base 5, and that would cancel out our base 5's here. So because these both have the same base, and that's what we're going to always try to make sure we get on these exponential equations when they're exponential like this. So all of these 3 right here are exponential equations. We're going to try to make sure our bases are the same so we can cancel them out and the exponents will equal each other. So that's what we're just going to do right now, just cancel out the base 5's. So that means that our exponents will equal each other. 2x plus 4 is equal to 5x minus 8, and now it's a simple, easy equation to solve. So let's just go ahead and finish that off. So I'll subtract 2 from both sides. So 4 on the one side is going to equal 3x minus 8. I'm going to add 8 to the other side to get the 3x by itself. And so now 4 plus 8 gives us 12 on one side, 3x on the other side now. And we just got to divide by our 3. And 12 divided by 3 gives us 4, so our answer, x is 4. Number 2, now this gets a little more challenging because the bases are not the same. So what we want to try to do here is try to get these bases to become the same base. So we want to break down the 4, break down the 8. So 4, we can break them down both into base 2. 4 is 2 squared and 8 is 2 to the 3rd power. So we're going to start with that. So starting with 4 is going to become a 2 squared. And then I'll put my exponent right there outside of the parenthesis, the 2x minus 1. The 8 is going to be 2 to the 3rd. So we'll break that down to 2 to the 3rd. The exponent there is x plus 2. Put that outside the parenthesis. So now we have the same base, base 2. And we have basically a power to a power situation where we would multiply the exponents. This 2 will multiply our 2x minus 1, 3 will multiply the x plus 2, and these will be distributive properties. So that's what we'll do there. So that will become a 4x minus 2 for that exponent, a 3x plus 6 for this exponent, and now the 2's can cross out. The base 2's cross out, and now we can just have our exponents equal each other, and we have another simple equation here to solve. So we'll solve this by subtracting 3x there from both sides. So that just leaves us with an x minus 2 on the one side equal to 6, and then we're just going to add 2 to both sides, and so that's going to be 8. So x will equal 8 on this problem. It almost looks like that's not a very good minus sign right there, you can see. So that should be at x minus 2 right there, and we're adding 2. Alright, number 3, this one's a little bit different. We have 3 to the x plus 3 equal to a 5. 5 doesn't even have any exponent that we can see. It would have a 1, but there's no way to get 3 and 5 to become the same base. They're already as small as they can be. They're already prime numbers. So in this one, what we're going to do here is we need to free the x plus 3. So I need to really get rid of the base 3 only, and that means I need to zap both sides here by log base 3. So starting with this one, if I zap this with log base 3, I will cancel out my base 3, leaving me just with the x plus 3 on this side. But whatever I do to one side, I got to do the same to the other. So I got to zap the 5 over here also with a log base 3, making that a logarithm on the right side. So x plus 3 is now going to equal log base 3 of 5. So our x plus 3 on the left side, that was freed because of the inverse property, canceling those out, and now we have a logarithm over here. Log base 3 of 5 gives us this. So what we need to do now is figure out what is log base 3 of 5. We can figure this out on the calculator with our change of base formula. So that was what we learned a couple lessons ago, or last lesson actually, in 6.5. So our change of base formula would be this. 5 would be on top, so we would change it to log base 10. And so log base 10 of 5 on top, log base 3, or I said log base 10 of 3 on the bottom. So remember, 5 is going to be on top, and then 3 will be on the bottom, both in log base 10. So now we can then use this to help us figure this out. And I'll do it on a calculator really quick. So let me pull up my calculator so you can kind of see this. So I'm going to use my log button down here, and I think I have to push the 3 or the 5 first. So 5 and then log, yeah, there it is. And I'm going to hit divided by, and then 3 and then log, 3 and then log. And it gives me that, that's the log base 3 number. But now equals, it'll give me this 1.46 number. So that's what we're looking for now. So that's our 1.46. Now I just got to solve this by subtracting 3. So subtract 3 and we're done. X will equal a negative 1.53. Okay, so continuing on now with just 4 through 6, still we're on the exponential equations, and we're trying to get the base to be the same number if we can. So here we have a 1/5 base, and in this one we have a square root of 25 to the x power. So whenever you see a radical, you really need to change it back to a fraction exponent. So remember, this would be the root is 2 on the square root, so that's your denominator. Your extra exponent actually is the x, so it's x over 2 for the exponent for that 25. So we can just do that real quick and just see that this here, square root of the 25 to the x, really is the same thing as this, 25 to a fraction exponent of x over 2. And so now we can try to change the 1/5 into a 5. This could be base 5. 25 also could be base 5. 1/5 could be base 5 with a negative 1, right? Because negative 1 is going to flip it. So 5 to a negative 1 is the same thing as a 1/5. So now we can say this exponent, 3x minus 2, is outside of that. Eventually we're going to multiply the negative 1 times this exponent. And over here we're going to see 25. That can be 5 squared, so we have a base 5 on this one. So 5 squared, and then we have the x over 2 exponent on the outside of this one here. So when I now distribute this negative 1 in, it's just going to change our signs here. When I multiply 2 times this fraction, it will cross cancel the 2's and leave me just with x. And so now I'll have this. Our 5's now can cross out because they're the same base, just like we talked about. They can do that because of the inverse properties. And now the exponents will equal each other. And so now we have this equation, negative 3x plus 2 is equal to x. So we could add the 3x now to both sides. And so it gives me 4x now on the other side over here. So 2 equals 4x. And then just divide by 4. And so 2/4 is what x is going to equal. 2/4 we would reduce down to a 1/2. So there's our answer for number 4. So you can see these are not too difficult to do. Just as you're starting it out, you just got to think about it. How can you get these bases to be the same base? So like on number 5 here, we have, first of all, on this one, we do not have the base by itself. This is a 12e. We want to get the e by itself. We need to get rid of the 12. So to do that, we're going to have to divide out the 12 first on this one. So divide both sides by 12. That cancels the 12s here. And now we'll have e to a 1 minus x here on this side, 500 over 12 on the other side. And so now what we want to do is get rid of the, obviously we're not going to be able to make this into a base of e at all. So this one's just going to require us to kind of zap it with log base e, or the natural log. That will undo the e base and release my 1 minus x. So I'm going to do that, zap it with the log base e so I can cancel out the base e. Whatever I do to one side, I have to do the same to the other. So we're going to zap this also with log base e as well. So our 1 minus x now on the left side will equal a logarithm with log base e, or natural logarithm, of 500 over 12. And so that's why I'm going to now change the log base e to ln. It's the same thing. And so now what we want to figure out is, what is this on this side? What is the natural logarithm of 500 divided by 12? We can use our calculator for that. So I'm going to hit figure out what this is here. So 500 divided by 12. Let's go ahead and clear. So 500. Remember, I got to push the number in first, then hit my ln button, which is up on top here. So 500 divided by 12, and that will equal this 41.6 number. And then I just hit ln. Natural logarithm of that is now 3.729 approximately. So that's what we're going to now see here. 1 minus x will equal about 3.73. I'll just round it there to 2 decimal places. Subtract 1 now from both sides. And so that's now going to give us a negative x on one side, negative 2.73, or I'm sorry, positive 2.73 on the other side, just basically 3 minus 1 there. And now we just got to change the sign of both sides so we have a positive x. So positive x will actually equal a negative 2.73 for our answer. And then number 6, so our last exponential equation to do here in our notes. First thing we want to do is get the e to the x power by itself. So we need to get that base part by itself. First thing we got to get rid of is our 14. Move the 14 over to the 11. So, first step here on all of these ones are making sure that you isolate your base and your exponent. So that's the e to the x power needs to get solved for first, and then we can then go off of our inverse operations at that point. So first of all, add 14 to both sides. So we're going to get 11 plus 14, 25 on this side now. So 3e to the x power is equal to 25. And now I can get rid of the 3 by dividing by 3. So divide both sides by 3. So e to the x power now will equal that fraction of 25 thirds. And we'll have the same kind of situation as we had over here. Get rid of the e with a log base e. So we're going to zap it with a log base e. That cancels out my base e. It frees my x. So now x is going to equal on this side. Whatever you do to one side, we got to do the same to the other. So we got to zap the other side also with log base e. That gives us a logarithm here. So x will equal the natural logarithm of this fraction. So natural logarithm, ln, for natural logarithm of the fraction. And we can do the same things we did on the calculator before. So I can just clear that right there. 25 divided by 3. That will give me this number, this decimal number, hit my natural logarithm, and there's my answer, 2.12 approximately. And so let's see, our answer there is right there, 2.12. That's what x equals. All right, our joke of the day. Here's one a little bit different of a joke of the day. It's not so much of a pun. It says, 2 lawyers walking through the woods spotted a vicious-looking bear. The first lawyer immediately opened his briefcase, pulled out a pair of sneakers, and started putting them on. The second lawyer looked at him and said, "You're crazy. You'll never be able to outrun that bear." "I don't have to," the first lawyer replied. "I only have to outrun you." That was a good one. Okay, let's move on. Our next core concept, page 181 again, just right below the exponential equations, are logarithmic equations. So here we see kind of the same thing, but now just with the logs. We're going to notice the same idea going on here. We can, if we have a log of the same base on both sides, So like I said, we were just going to we can do this. Here on the example, you can see it. Log base 2 of x equals log base 2 of 7. They're both the log of the same base. They're both log base 2. So I could undo these logs if I zap them basically with a base 2. So base 2 can cancel out log base 2, and whatever you do to one side, do the same thing to the other. So base 2 cancels out log base 2, and so now that frees the x here from that logarithm, frees the 7, so x equals 7, just like it says that it does right there. So if you have a logarithm of the same base on both sides, so you have to make sure you're down to a single logarithm though. So you have to only can have one logarithm on each side, and if it's the same base there, obviously it should be the same base. You can then just cancel out the logarithms, and then whatever you have here can be released, and you can set those equal to each other, and sometimes you might have to solve some more after that. Sometimes you guess that's your answer like it is here. Okay, so back on page 182, 7 to 9, in these equations we have logs. So these are log equations. It does say to check for extraneous solutions. The reason for that is because we need to remember that the logarithm here, this part has to be a positive number. So it cannot be less than 0. It cannot be 0 even, so it has to be greater than 0. It has to be positive. So let's start with number 7. We have 2 equals the log base 3 of 4x. So what we can do here is there's a couple ways we could do it. We can get rid of our log to free the 4x by zapping it with a 3, right? Giving this a base 3, doing inverse properties, and we can do that, which means I can give this over here base 3, which would be 3 squared, and that would be one way we could do it. Another way you could do it is just also you can change it from the log form into exponential form. Since it only has log on one side, we can do that with log equal to a number. So that number would be the exponent here for 2. So 3 to the second power will equal our 4x. And so we can write that down. 3 to the second power will equal 4x. And then 3 squared is 9. So now we see this is actually really going to be 9 equals 4x. And so now we see 9 equals 4x. We just want to divide by 4 to solve for x. And do that. 9/4 is our answer for x. That's it. 9/4. So that's the way you can, kind of do log equations a couple ways, either changing it from log form to exponential form. But that's only if you have log on only one side of the equal sign, and on the other side you just have a number. Otherwise, you would want to do the inverse properties. If you have logs on both sides, like we'll see here on number 8, which we do, ln is on both sides. So we can now, this is base e, log base e. So we could think about zapping this with an e, base e, which will cancel out their logarithms. So these logarithms here can cancel each other out, which means we're just going to set these two parts equal to each other. So this x squared plus 3 will equal our 4, because these logs here are going to cancel each other out. So now it's just going to be that x squared plus 3 equals 4. Let's go ahead and subtract 3 from both sides. And actually, I could subtract 3 from both sides, I should say. We could do it either way. We could subtract 3 from both sides and get 1 on this side, or I could subtract 4 and get now -1 equal to 0, because it is a quadratic. So we can think of it as, as a quadratic where you have x squared minus 1 equal to 0, set it equal to 0, and then factor it. So here at this point we have two ways we could do this as well. We could use factoring to solve this, or we could use the square roots to solve it. And I'll show you both ways, but this way is the factoring way, where we want to set it equal to 0. So I subtracted 4 from both sides to get my -1 over here. And now this is a difference of squares, which would factor to x plus 1, x minus 1. Okay, just x and x up front from the x squared. 1 times 1 from back there, 1's plus, 1's minus. And now we just set each one of these equal to 0 separately and then solve. So our answers here really are just going to be x equals a -1, x equals a +1 for the two answers on this one. We're getting two answers from a quadratic. And so the other way we could do this, like I said, instead of, we could have got the 1 on the other side. We could have subtracted 3, and now it could have said x squared equals 1. So it could have been like this, x squared equals 1, and then we could take the square root of both sides, where we see x now is free from the square root sign. So x is by itself, and now we have a plus or minus. Here's where we have to put plus or minus in front. Square root of 1 is 1, so we could say plus or minus 1. This is the same thing. So either way, we see that we're going to get a positive 1 and a negative 1. And it does say check for extraneous solutions. We would want to check these because one of them might be extraneous. Well, if I plug in 1 or negative 1 into where x is here, I'm going to get 1. So negative 1 squared is 1, 1 squared is 1. That's going to be 1 plus 3, which would be 4 here, so that's okay to have. So you have a natural log of 4, which is fine. As long as it's a positive number, then you're okay. That's what I put here. This is giving you natural log of 4, which is fine. So both answers are going to work on this one. There's no extraneous solutions. Number 9, here's one where it's got a log on one side equal to a number, so you can say 8 to the 2/3 power is equal to this part here. Or if you want to just think of zapping it with an 8, cancels that out, so this will equal 8 to the 2/3 over here. So however you want to kind of think of that, it's in one of two ways. So we're going to get 8 to the 2/3 power, that's what we need to know. 8 to the 2/3 power will equal our number part here of x squared minus 5. Like I said, we can also think of it as giving this an 8, zapping this with 8 here, canceling the 8's out, and now this over here is also 8. And then whatever you do to one side, do the same to the other side. So base 8 to the 2/3 power. Base 8 to the 2/3 is equal to this now. This is now free from the logarithm. And so we want to figure out, okay, what is 8 to the 2/3 power? We want to put that back into kind of a radical. So the root would be 3. So it's a cube root of 8, and then we could square it. So we can kind of think of it as that. Cube root of 8, and then we can square that. That's going to equal our x squared minus 5 here. So the cube root of 8 is 2, and 2 squared would be 4. So this number here, 8 to the 2/3 power, is just 4. So it's 4 is equal to x squared minus 5. Go ahead and add 5 now to both sides. And so that's going to give you 9. So we have x squared is equal to a 9. Take the square root of both sides. And so the square root of 9 is 3, but here's where we're going to put plus or minus. So x equals plus or minus 3. And so you'd want to check that one as well. So it's going to go in where x squared is. So whether it's a 3 squared, that's going to give you 9, or negative 3 squared is also going to give you 9. Either way, you're going to get 9, and 9 minus 5 would give you a 4. And that, again, is going to be okay. So as long as this is a positive number here, you're going to be fine with your answers. So no extraneous solutions there either. Okay, so number 10 and 11. These ones are going to take some properties to be able to simplify. We need to make sure that each side of the equation has only one single logarithm. So you can see on number 10 we have 2 here with an addition sign between them. So we need to put those together with our properties that we learned in 6.5. So this would be the product property with the plus. We need to multiply the x times this x plus 2 part here, and then that will equal this part on the right side. So now we're going to see x times x plus 2. You can just show it like that. We will distribute that eventually. But now we have the natural logarithm on one side, the natural logarithm on the other side. So there's where we can cross out those natural logarithms. And now these will just equal each other. So these parts here are now our equation. They're going to equal each other. And so we're going to see if I distribute this x into here, it's going to be x squared and then a 2x. So we're going to get x squared plus 2x is equal to, now this side is x plus 6. And since it is a quadratic, let's go ahead and get it equal to 0. Let's subtract x from both sides. And then we can see we're going to eventually get an x on this side here. Let's also subtract 6 from both sides as well at the same time. And so we're going to cancel out these on this side. On this other side we get an x squared, a 1x, and a minus 6. So there's our trinomial there on the left side, equal to 0, because these are canceling each other out. And so now this trinomial we can factor to 2 factors, to 2 binomials. And so we want to use kind of just the blank binomials. We're going to say x squared goes into both of them as x times x. So x is up in front, or this is the simple method. So x times x. And then what two numbers multiply to give us 6, that subtract to give us a 1. That would be a 3 and a 2. So we're going to get 3 and 2 back here. Since it's a negative, they have to be different signs here, 1 plus 1 minus. And the bigger one will be the plus, so 3 is a little bit bigger. It's going to get the positive, 2 gets the negative. You can always check that with FOIL to make sure you're correct. Now each one individually will get set equal to 0, so x plus 3 is equal to 0, and then we can just solve that by saying subtract 3. So x equals a negative 3. And the other side, the x minus 2 will equal 0. And then just add 2, so x equals 2. And so here's where we get two answers. We do want to check them just to make sure that there's no extraneous solution. So if I try putting 2 in, I'm going to see 2 goes in here. That's going to be natural log of 2, which is fine. As long as it's positive, it's okay. In here, it's going to be 2 plus 2, which will be 4 here, and this will be 2 plus 6, which will be 8. So we're getting this basically, natural log of 2, natural log of 4, natural log of 8, all positive numbers, and that's fine. So that means that 2 is an acceptable answer. So we can keep the answer for 2. But if we plug in -3, as soon as we plug it into here, natural log of -3, no, we can't have that. Okay, that cannot be a negative number. It can't even be 0. So it has to always be a positive number, so which tells us that this one, -3, is an extraneous solution then, and we can't keep it. So the only answer there for this problem is just the 2. Number 11, we got another one. We have logarithms on both together here on the same side, so we got to put these two together with the property. This would be the quotient property with the subtraction, which means we need to make this into a fraction. So this will be our numerator, x plus 5. Our denominator will be x minus 2. And so we want to start with that. So log base 2 of the fraction. So log base 2 of this fraction. There's the numerator, there's the denominator. So we got to condense it down into the single logarithm, and it will equal the 3. So it equals our 3. So now we could either zap it with 2, that's one thing we do, so it's 2 to the 3rd power equal to this fraction here, or just we can think of it as base 2, 2 to the 3rd power equals the fraction. Either way, we know we're going to get 2 to the 3rd power equal to the fraction. And 2 to the 3rd we know is 8, so it's really 8 is going to equal that big fraction. And so what I want to do here is I'm going to put this 8 into a fraction form by just putting 1 underneath it, and then what we can do is cross multiply. If you have fraction equal to a fraction, you can always cross multiply. So 8 times the x minus 2, 1 times the x plus 5. So as we do that, we're going to get 8 times x, which is 8x. 8 times -2 is -16. So 8x minus 16 on one side. 1 times this x plus 5 is just x plus 5 on the other. And now we can just solve this one. We could subtract x first from both sides, and that would give us a 7x minus 16 equal to 5, and then just add 16 to both sides after that. So now 7x is equal to 21, and then just divide it by the 7, so x equals 3. We can just double check that that's a good answer. We're getting 3 plus 5 is 8 here, 3 plus 2 is 1 here, both positive numbers. So 3 is acceptable, we can keep it. Alright, so we're going to switch gears here. On page 183, we're now going to switch to inequalities, solving inequalities. That's at the top here, and I'm going to add a couple more in just as some practice. It only gave us 1, and I wanted you to see a little bit more of this. So it's got log, this would be base 10, remember. Log base 10 of x is less than or equal to a half. So what we could do there is we could zap them, and I would do this. I would always try to do the inverse property for definitely the inequalities with the logs. So that's always going to be the best way to do it. So we're going to change this now to just 10. I'm going to put 10 here. That's going to cross out my log, and I'm going to put 10 over here for the 1/2. So we're going to see 10, and then this is log base 10, so those cancel out. I freed my x, and we do the same thing to the other side. Give it a base 10, so 10 to the 1/2 power. So now I have x is less than or equal to 10 to the 1/2 power, and we just need to remember that 1/2 power is the same thing as saying the square root of that number. So it's just x is less than or equal to the square root of 10. That is not the final answer, because remember, if we have an inequality now this is a range. It's just saying that x is less than this square root of 10, which is somewhere about 3 point something. But remember that x cannot be, in this problem, x cannot be anything negative or even 0. It has to be positive. So that's what this is saying down here. I've reminded you the definition of a logarithm. It says let b, which is the base, and y, which would be actually this part here in our problem. See, there's the y. It's our x in this one. Be positive real numbers. They have to be positive real numbers. So that means it cannot be less than or equal to 0. And so that's what we want to remember here, is that x has to be greater than 0. We need to remember that it has to be greater than 0. It cannot be less than or even equal to 0. So we got to include that part in our inequality answer. So I'm going to make this like this now. So x is in between 0 and this square root of 10. I do not put the little equal to line because it cannot even equal 0. just has to be, x has got to be greater than 0. So that's what we got to do when you have a less than sign here. If you have a greater than sign, then we don't have to worry about it at all. So if it's greater than, don't worry about it. Number 12a, let's go and look at this one. This is an exponential one. There's no log here, so it's an exponential one, but it does have 10 and 3, which you're not going to be able to do this one without zapping it with a logarithm. So we have to zap this with log base 10. I'm just going to put log there. That will cancel that out, freeing my 2x minus 6 greater than, and then this one's going to also be log here of 3, so log 3 on this one. And so we want to figure out, well, what is log 3, and so we want to use our calculator for that. I'm just going to hit 3 and then the log button, and that gives me this number, 0.477. So 0.477, so 2x minus 6 is greater than 0.477. And now we can add 6 to that on both sides. And so we say 2x is greater than this now, so it's going to be we're going to add 6 to this, so it's going to actually be 6.477, and now just divide by 2. So dividing by 2, let's grab that calculator again. So I say adding 6, I added 6 to this, and now I'm going to divide it by 2. And it equals 3.239. Let's go 3 decimal places. 3.239. So 3.239. That's what x is greater than. So we don't have to worry about anything on this one as far as this part's concerned. That's only for the logarithm that you have to worry about, and that you need to make sure that x is a positive number. X here can be a negative number. It's okay to have negative exponents on the exponentials. This one, 12b, go ahead and write this one down. So this one has, we got to first get the logarithm by itself, so I got to subtract 9 from both sides first. So that way I got log x is less than 45 minus 9, it's 36. And so now I'm going to zap this with 10. This is log base 10, so I'm going to zap it with a 10. Let's go use a different color here, so 10 here. Cancels this out, frees my x here, less than, and this is going to be 10 to the 36th power. 10 to the 36th power. And here, again, because it's less than, we have the same situation as we do here. We're going to have to put this in front. So we're going to have to put it like this then. I'm going to put greater than sign or less than sign like this. X is going to be greater than 0. So that's my final answer. I'm leaving it with 10 to the 36th power. I'm not going to figure this out. That's going to be a huge, huge number, so they're going to be okay with leaving it as 10 to the 36. Okay, so number 13, this word problem. Does your parents buy juice for your graduation party and leave it in their hot car? When they take the cans out of the car and move them to the basement, the temperature of the juice is 85 degrees Fahrenheit. The room temperature of the basement is 60 degrees Fahrenheit, and the cooling rate of the juice is R equals 0.0147. Using Newton's law of cooling, how long will it take to cool the juice to 63 degrees Fahrenheit? So first of all, what is Newton's law of cooling? Well, I'm going to give that to you right here. That's a formula, and that's what this is. So it's T equals T of 0 minus T of R, the E, our natural base E, minus RT, rate and time there, plus T of R. And so we have the temperature, T standing for temperature here. So you have your initial temperature, that's the T of 0. And then we have our room temperature, basically. That's what we got here. T of R is like room temperature. And so our final temperature here that we're trying to get is just the T. So let's go ahead and fill things in here. So the T right on this side is our final temperature. That's the 63 degrees that we want it to become. And so 63 is equal to the starting temperature. The initial one is 85 degrees. The juice is 85 degrees. So that's going to be 80 minus the room temperature right here, 60 degrees in the basement. So minus 60, and then we're going to put our E, our natural base E, minus a negative R. So our R is this number decimal, and we're trying to find T on this one because it says how long. So we're looking for time, and we're looking for this T right here. And we still have this plus the room temperature number again, so that's the 60 again, so plus 60 there at the end. So now we just need to solve this for t. The first thing we want to do is move that 60 to the other side. So subtract 60 from both sides. It cancels it here. 63 minus 60 gives us 3 on the other side. And we're also at the same time getting 80 minus 60 to become 20 there in front of the e. And so this is kind of like the PERT formula, P-E-R-T in this sense. We have a 3 right here. And so we're trying to solve for the t. First thing we want to do now at this point is get the e by itself to this exponent, so divide by 20. So divide out that 20. 3 divided by 20 is a decimal. It is 0.15. So I'm going to make that 0.15 is equal to e to our exponent here. And so now I need to release, basically I need to undo base e. To undo base e, I need to zap both sides with a log base e, or natural log. So I'm going to zap this side with the natural log, ln of our 0.15. And then do the same thing on this side. Zap it here, log base e will cancel out base e, and now I'm going to be able to be free with this number as my exponent. So now as I was thinking about what is natural log of 0.15, so let's go ahead and look at our calculator again. So natural log, let's make 0.15 and hit natural log. It's this number, it's negative 1.897 approximately. So let's go ahead and put that over here. I'm going to do that up on the top now. So that's my natural log of 0.15 is this number, negative 1.897, and it is equal to that exponent. The exponent that we had here, this is now free. All I got to do to solve for t is just divide by this negative 0.147 number. So let's divide out by that number. These now cross out, and I've solved for t. So on the calculator, let's bring this back up. So there's my negative 1.89 number. I'm going to hit divided by 0.0147 and make that negative, and it equals 129.0, let's round this to 0.06, let's go 2 decimal places. So that's going to be 129.06 minutes. That's how long it will take the juice that's 80 degrees in a room that is 60 degrees to cool down to 63 degrees. Okay, number 14, our last problem for the lesson. So it says an earthquake intensity is measured by the formula R equals log, and we have I standing for intensity over I of 0. So I of 0 is like the initial intensity, or the smallest intensity you can think of, or possibly be. Where R is the Richter scale rating of an earthquake, I is the intensity of the earthquake, I of 0 is the intensity of the smallest detectable wave. Sorry. In 1906, an earthquake in San Francisco had an estimated measure of 7.8 on the Richter scale. In the same year, another earthquake had an intensity level 4 times stronger than the San Francisco earthquake, giving it a Richter scale rating of R2 equal log, and then 4 times the I up on top is different. So you can see that's the part that's different on this formula on here as to this one. So what was the Richter scale rating on a 1 to 10 scale here, on a scale of 1 to 10, of the other earthquake? So what we want to do here is we want to look at this part right here, seeing that as as a property we can use. So we're multiplying 4 times I up here. That's a product property where we can break that now into 2 logarithms. Let's see where my pen is. So we're going to use our R2 here is equal to log, and we're going to do 4. So I'm going to do log 4 first, and then plus log of this I over I of 0. I can keep that in a parenthesis there. So now what we know is that this earthquake here, the San Francisco one, measured 7.8 on the Richter scale. That is the same thing as what this is. So that's what our Richter scale is here for that one. This one's the 4 times larger than that, so that's what the 4 here is for, log base 4. So we did our property, but now I can substitute 7.8 for this, because that's what it is. 7.8 is what this logarithm equals here from the San Francisco earthquake. So now we can say R2 and log 4 plus 7.8. And now we just want to figure out, okay, what is log 4? So again, go back to our calculator, I'm going to hit 4, my log button. It is 0.602. Let's just say 0.6. So R2 is equal to 0.6 plus 7.8. I just went 0.6 because that was only one decimal place in 7.8. So now we just add these together. R2 is equal to 8.4. And so there's our answer, 8.4. There's our scale from 1 to 10. So it says, what was the Richter scale rating on a scale of 1 to 10 of the other earthquake? It was an 8.4 earthquake. Alright, so that concludes our lesson for 6.6. And so you want to go on to doing the assignment now for 6.6 on Big Ideas. And I'll see you back in class.